Hello everyone and welcome back. Today we're going to be looking at Taylor series, in particular examples of Taylor series. And I want to remind you that the general form of a Taylor series is just a bunch of coefficients attached to a bunch of powers of x or x minus a if I'm centering somewhere other than 0 in general. What that often gives us here is an interval of convergence centered around a, characterized by a radius. So it's generally running from some value a minus r to a value a plus r, representing a radius of convergence r for our interval of convergence I. All right, so that's what we're looking at. Now, I want to bring back one of the examples that we looked at last time, because I know you think like, why can't we just stay at 0? Because there's some things that just don't belong at 0. And one of the most common things is, well, what if it doesn't actually exist at 0? What if the function doesn't exist at 0? That would be a good spot. Maybe we shouldn't expand at 0, right? And one of the standard examples is the log function. And to keep it clear what's going on with this, I attached the graph. Remember, the log of 1 is always 0, so we always have the point 1, 0 on the graph. And for any value less than 1, the logs are negative, heading for negative infinity as we get closer to as x gets closer and closer to 0, the log gets closer and closer to negative infinity. On the other side of 1, it's going to increase slower and slower and slower. And depending upon where the base is, it will cross the y equals 1 line at the value of the base. And for the natural log, that base is e. Okay. Now, last class, we developed an expression, a power series, for log of x, which looked kind of like this. It was x minus 1 minus x minus 1 squared over 2 plus a third of x minus 1 cubed minus a fourth of x minus 1 to the fourth, on and on like that forever, right? And with a general term that looks like, well, it's either be positive or negative, and it'll be positive when n is odd for the odd powers, and it'll be negative for the even powers, as we see here, right? Negative at even, positive at odd. And also remember that to find, we did this by taking a derivative and then integrating, and when we integrated, we ended up with a constant of integration. By plugging in 0, we were able to discover, on our expansion, we were able to discover that actually by plugging in 1, because we had x minus 1 powers, right? By plugging in 1, we were able to see that the constant of integration was the log of 1. Okay? Which is nice for this one, because that just gives us 0. What we didn't look at in our last class was the radius of convergence, and I want to take care of that oversight today, and also let that work with us in the class. Now, with most of these power series, and I'm not sure I have any examples where this wouldn't be true. In general, you just assume that if you need to find the radius of convergence, you need to use a ratio test. And then if the radius ends up being anything other than infinite, well, then we'll go ahead and set up the radius of convergence and then check the endpoints. Okay? And when you do these, you'll almost always find the radius will either be infinite or 1. Because, you know, how do the tests end up working? The tests end up working using a ratio test, and the ratio test always compares the ratio to 1. And we have the absolute value of some expression equal to 1. Less than 1 is converging, greater than 1 is diverging. We go from there. In this particular case, we can go ahead and use the ratio test by looking at the n plus first term, right? Look at the nth term here. We're going to add 1 and add 1. And I guess we could add 2, but I'm not going to worry about this because the ratio test uses an absolute value. And when we're looking at absolute value, nobody cares. Nobody cares. For absolute value, so I'm going to avoid that. So I'm going to look at the n plus first term by adding 1, and divide it by the nth term, which is just this. And that's the ratio that I'm going to use for my ratio test. So here we go. The n plus first term is going to be that x minus 1 to the n plus 1 over n plus 1. Good to see you, David. As soon as you actually joined, I see he's joining. And I'm still missing people. Okay. And here's the nth term. You take care of the x minus 1, n plus 1, n plus 1. That just gives us an x minus 1. Now, here is one of the most important things to pay attention to, and that is when we talk about these limits on these, we're always talking as n goes to infinity. So when I generally talk about L infinity, that's because there's only one variable you have to worry about. It needs to be very clear here that x is not the thing that's going to infinity here. N is. So as far as n is concerned, as n goes to infinity, x is a constant. It comes straight out. You don't have to pay attention to it. Just bring it out with the absolute value and there you are. So when I take the fraction x minus 1, everything it cancels except for that last plus 1, and that will come out. And what do we have left over? The n will come up, the n plus 1 comes down, and we're looking at the limit approaches infinity of n over n plus 1, which everyone knows is just 1. Right? And just anal enough, I didn't like the way my infinity looked, so I'm going to write that again. Infinity, that's better. Okay. And so what we have is the ratio itself of the n plus first term divided by the nth term is the absolute value of x minus 1, or the absolute value of that ratio is. And we know from the theory that this will converge, just like any other geometric series, when x minus 1's absolute value is less than 1, and diverge when the absolute value is greater than 1. That defines an interval. Here's Anthony coming, yay! That's 10, it's just Deborah I'm missing now. Just Deborah I'm missing now. Welcome, Anthony, make sure you answer the poll. And the stuff that you missed, just a couple minutes right there, you could just watch the couple minutes of on YouTube, and that shows up later this afternoon. So what we have here is a radius of convergence of 1 on this, which gives us an interval of convergence centered at 1 from 0 to 2. Okay, so let's back up so we can see the original function again, and then check the endpoints. So by checking the endpoints, I'm just going to plug in those endpoint values into the original series and see what happens. So let's look what happens when I plug in 2. Okay, I'm going to plug in 2 up here. If I plug in 2, x minus 1 evaluates to 1. And so I get 1 minus 1 squared, which is 1, over 2, plus 1 over 3, minus 1 over 4. So what you see is this alternating harmonic. 1 minus a half, plus a third, minus a fourth. Now, you look at this. It's alternating, right? And so the first thing you do is to make sure that the nth term goes to 0. Does the nth term go to 0, guys? Does the nth term go to 0 on these? Yes, no? Yes, no? Type yes for yes, no for no. Thank you, Osmaldo. See? Yeah. So, you know, the elf tank has weighed in Spanish. Yes, that's 3 of you guys. I want to make sure everybody's with me and interacting. And so I've got 3, and I'm kind of missing 7. 4, 5. Thank you, Patrick, David, Timothy. 6, 7. 3 more. 3 more. 8, 9, 10. Yay! Thanks, guys. All right, so everybody's in here and ready to interact with me, and I can't tell you how important that is. Okay, um, I try not to let it see, but I mean I spend most of my time in class when I'm seeing you guys, just stressing, looking for the one face that shows some confusion, and if I don't have that, that's your way of interacting, because you don't have to do a whole lot with that when I'm seeing you guys face to face. There's going to be the interaction because I am always scanning your faces to see who looks a little bit confused or whatever. I can't tell you how many times I've spotted an arithmetic error because Lourdes's face squinches this tiny little fraction of a micrometer. and I came to depend upon that actually. Now I actually have to watch my own arithmetic. Personally attacked? No, girl. You were like my hero. You were my hero. I mean, I was personally attacked. What does an elf tank care about somebody attacking? You just kind of like go out there and conquer, don't you? All right. Yeah, but that was useful. That was useful. And yeah, and the other things, just trying to see who's got what. Students like do the poker face sometimes, the professor doesn't understand it. But for the most part, because I don't let you know that I'm doing that, you'll just have natural reactions that helps out. Of course, that extra attention I put on that is why the arithmetic errors are happening anyway, because I'm paying attention to your faces, not what I'm writing. So there we are. Now I said I could plug in at 0 as well, right? If I plug in at 0, this term just becomes a -1. And you get powers of -1. But the powers of -1 are alternating. And what it means is it eliminates the alternation. Yeah, everything ends up being negative, but you still end up with -1 plus a half plus a third plus a fourth. And that is the harmonic series, which we know diverges. So we know that the endpoint at 2 converges because the nth term goes to 0 and it's alternating. That's all we need. So it converges by the alternating series test. We know the alternating series diverges by the integral test, but frankly, it's enough just to recognize that it's a harmonic series because it's that well known. Just recognize, if you just spot out, if you're mentioning this on an exam or something like that and you wanted to show your work, you just say, it's the harmonic series, it diverges, because it's that well known, right? Just go like, they're in Colorado, it's in Denver. Denver, well, it's in Colorado, that's all we need, right? Yeah, you had a question, Ryan?
Yeah.
Oh, I checked, by the way, I checked on the YouTube video, and your voice was coming out on the YouTube video, but it's apparently not working with my speakers well enough for me to hear. So you came out clear on the YouTube video, but I don't know, it's just not showing up, it's not coming up loud enough on my speakers here. So that's a problem. I can hear you right now about like this level.
Oh.
Yeah, I can hear you, but just barely.
I'll put it in the chat.
Go ahead. Yeah, it's the speaker on my tablet. It just doesn't go very loud. And I can't use the speaker on my laptop because then we'll get feedback. Or you won't hear me because I'll be using the microphone over there, and that's too far away from where I'm speaking. Okay, but go ahead and speak up and probably hear you that way. While the harmonic series converge in the alternating series test, but diverge with everything else. The harmonic series is actually, formally, it's this, the 1 plus a half, always plus, 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 and that diverges. This is not a true harmonic series, it's an alternating version of the harmonic series. Okay? And so the idea is if it alternates, then you actually get that it actually occurs. Okay? And one of the things I did cut out, oh well, is the actual proof of the alternating series test. But I'll be introducing that when we look at estimations on Tuesday. But yeah, the alternating series test, we know using estimation theory that the error from the whole sum and the next one right there, whatever this adds up to on any alternating series is always going to be less than everything that follows the negative 1/4 is going to have an absolute value less than 1/4. Everything that follows the 1/3 is going to have an absolute value when it adds up is going to have an absolute value less than 1/3. And that's going to allow us to be able to do estimations. And so in particular, I know everything that's missing after a particular term right there is always going to be less than that particular term. And so I know the remainder adds to 0, and that's enough to show me that it converges. Okay, now this next little bit, I wanted to toss that in here. And this is a nota bene. You still don't find out how it diverges in general. It looks like the bottom just gets bigger and bigger, forcing it to 0. Yes, it does, but the integral test says otherwise. Okay, the harmonic series diverges because of the integral test, right? Let's look at that. What, just integral test 1 over x from 1 to infinity. What do you get? Yeah, that's log x. 1 to infinity. The one, it just goes to 0, but the other one is the limit of log x as x goes to infinity. Yep. I probably said that too quickly, but there it is. I mean, the integral says this. You're looking at what, 1 over n, right? At 1 over n, that's equivalent to 1 over x as a function. Yeah, so yeah, it's just immediate on that. And I'll just leave that 1 over x because we know that into the notes like that. Okay, but I'm saying that nota bene, this, what you saw right there with the x minus 1s, people don't like expanding over anything over x. And so they cheat it by, instead of taking the function at x, they take the function at 1 plus x. Whoop, undo, I don't want to erase. At 1 plus x. Look what happens here if I replace x with 1 plus x. If x is replaced with 1 plus x, this x becomes 1 plus x. You get 1 plus x minus 1. Ah. Yeah. And that means you can get a Maclaurin series on this. And again, that log 1 is showing up. I wanted to have that in there, even though it's 0, because that's the term that's missing. That's the term that's missing. And after that, it's x minus x squared over 2, everything else the same. Now, I want to point out that the radius is just 1 on this. This is only converges to the function between 0 and 2. Even though the function log 1 plus x, has values, what, from negative 1 on to infinity. Now, the same is true for the log 2 plus x function, and that's how you would do these. So if I wanted to find the log of something bigger than 1, bigger than 2, I should say, I'd need to use another function. And again, this is all nota bene. I'm not going to prove these things, but it follows the same thing. But what ends up happening with this, you take the derivative of log of x plus 2, it becomes 1/2 over 1 plus x over 2. And so you get powers of 1/2 coming out. You get 1/2 times powers of whatever. And so you'll see x over 1 times 2, x squared over 2 times 4, x cubed over 3 times 8. This converges pretty quickly. This converges very slowly. Anything bigger, it's going to converge much more quickly, because now you're seeing like these powers going up really fast, not just dependent upon the 1, 2, 3, 4, but dropping also at powers of 2. And for alternating series test, yeah, the alternating series test, the remainder right there is going to be like less than 1 over half here, and the remainder here is like less than 1 over 8th. And then from 3 to 24, 4 to 64, it goes fast. Of course, you do have a problem that you have this log of 2, so if you want to find use Taylor series to find the log of 2.5. You can't use the log of x function because it doesn't converge in that region. And you can use the log 2 plus x function, but then you got to know what the log of 2 is. So not as useful. The thing I wanted to point on these is that when you do these changes, it often changes the radius. For the log of 1 plus x, the log of x functions, the expansions we had, the radius was 1. And for the next one, I just need to make sure, because the substitution turns it around, I end up not expanding in x over 2 rather than x. That's why it converges more quickly. But then the radius is 2. For log of 3 plus x, it will converge depending upon the value of x over 3, and the radius will be 3, and that will continue on. So that's one of the unusual examples where the radius is not just 1 or infinity. Okay, so now I think it's a good time for us to bring ourselves in treating the binomial series. Now, to be clear, what we're doing is we're talking about powers of a binomial. Okay? This is a binomial, 1 plus x, and we're going to take it to a power. Okay? And we're going to find the coefficients of the series, the Taylor series for f of x, by looking at its derivatives. You remember how we did this before, right? We think of f of x just generally as some coefficient plus a coefficient times x plus a coefficient times x squared, x cubed, etc. like that. All right? And then we take derivatives for the function that's r times 1 plus x to the r minus 1. That's really easy, right? Binomials are really easy to take the derivative on, right? Bring it down, subtract by 1. Now, I want to point out that this works independent of whether r is a whole number or a fraction or a negative number. And though we won't look at it, it also works for complex powers as well. But yeah, and so no matter what r is, whether it's a whole number or positive or negative, fractions or whatever, this will come down and get subtracted by 1. So for example, this was a half. We get 1/2 to the negative 1/2, right? But then as a power series, I just take the derivatives. C1x becomes C1. C2x squared becomes 2C2. C3x cubed becomes 3C3 x squared. The next derivative, the r is still there, and then an r minus 1 comes down, leaving with an r minus 2. Over on the series side, the C1 vanishes, 2C2 comes down as a constant, 3 times 2 C3 comes down, 4 times 3 C4 comes down, but now the x power is 2 less, right? I got 2 constants and down 2. And if I were to continue, I get 5 times 4 times C5, x cubed. The next derivative, and the last one I'll do in this little sequence, the third derivative is going to bring the r minus 2 down, along with the r and the r minus 1, and replace the r with r minus 3. This is very standard stuff you've done before, right? I'm at 9 students. I was up to 10 there for a little bit. Who's the one person who never showed? Deborah. I haven't seen Deborah all day yet. Yeah. And I know some of you guys are having connection problems. Kayleen just popped out. Yeah, we'll do with what we can. All right. So, on this one, the 3 times 2 comes down times 1, and 3 times 2 times 1 is just 3 factorial. As a matter of fact, 2 is 2 factorial. As a matter of fact, 1 is 1 factorial. As a matter of fact, 1 is also 0 factorial. Keep that in mind for a moment. But the idea here is by the time I'm getting the third derivative, I'm going to have 3 numbers out in front of the coefficients. 3 numbers in front of the general coefficient. Here was 3 factorial. Here I got the 4, came down, times 3 times 2, 4, 3 times 3 times 2. The next one is going to have 5 times 4 times 3, c to the 5th. I mean, for the 5th coefficient, c5. And of course, this is no longer x to the 5th. It's come down 3 times to the 2nd power. And the next one that I'm leaving out is 6 times 5 times 4. You get 3 of them. Every time you take another derivative, you get another factor out in front of the 1 plus x. And the power drops by 1. Now let's look at this a little more and actually figure out what this means in terms of the coefficients. We can find all of these coefficients just by plugging in 0. And if I plug in 0 into the original function, I get just 1, right? And that's going to be the first coefficient, C0. If I plug in 0 into the first derivative, I get r times 1 to a power, but that's just 1. I get r. And that's just going to be C1. For the next derivative, when I plug in 0, I'm going to actually get 2C2, or 2 factorial C2. And that's going to give me the second derivative at 0. And if I plug in 0 for the second derivative, I get r minus 1, and 1 to a power. So what's happening each time is I end up with 3 factorial C3 as the third derivative at 0, which is also these 3 factors, starting at r, dropping 1, dropping 2. I didn't drop 3 here, r minus 1, r minus 2. That's because I start up with r minus 0. I have 3 factors here. It ends up at r minus 2 because I started out at r minus 0. 3 factorial times the third coefficient is the product of these 3 factors. Yes, you can see over here there's something really big I'm going to be talking about when we're done to summarize on this page. But now I want to take a look at the radius, and I'll tell you what the answer is just to start with. Yes, the radius is 1. For binomial series, the radius is 1. Okay? And I'll put a little asterisk on that in a little bit right there, because that changes a little bit, but you don't have to pay attention to it. Now, to be able to see the radius, I went ahead and I wrote the n plus first coefficient term, just in the same form. When we get to looking for the coefficient of the n plus first term, that's going to be n plus 1 factorial times n plus 1 terms, right? And since it's n plus 1 terms, I'll end up at r minus n. Yeah? Because I ended up with 1 less then, right? 1 less than n plus 1 is n. And the one before that was like r minus n minus 1. Yeah. Just go ahead and understand. This is r minus n minus 1. And people don't normally write r minus n minus 1. They just write r minus n plus 1. But the thing being subtracted there is actually less than. This is like r minus 3, and that's r minus 4. Okay? R minus 4 plus 1, R minus 3. Undo. Undo. There we go. Yeah, so that might look a little bit unusual to you. This might look a little bit unusual to you, but it's only because the minus minus. The n factorial term, the nth term is n factorial times c sub n. And that's going to be all the things except for that last one, because this had n plus 1 terms, n plus 1 factors, and there's the n plus 1 factors. And the first n factors are the same. It's just this one's that's missing. So when I divide these out, the n plus 1 term looks like c sub n plus 1 x to the n plus 1, c sub n over x to the n. That's the ratio we use for the ratio test. Look at the x. That just comes out because we're looking at n, the limit as n approaches 0. And what's left? Look at limit at infinity of r minus n over n plus 1, the absolute value. Well, r is a constant as n goes to infinity. As n goes to infinity, this just looks like negative n over n. or just n over n if I'm looking at the absolute value. This is just 1. So as n goes to infinity, the radius, the ratio of the n plus first term divided by the nth term is just the absolute value of x. And by the ratio test, that converges when the absolute value of x is less than 1. In other words, the radius is 1. Now, because this is a finite case, a finite interval, you would normally test the endpoints. And we could test the endpoints. Fun fact, the convergence of the endpoints depends upon what the power was. And I could spend a lot of time on that tiny little finicky detail as to what happens for different values of r, but I'm not going to. Just, it's enough to know that it converges inside without knowing what's happening at the endpoints. Okay, now you saw all these things happening, right? I got these factorials happening over here and these powers coming over here, and that looks kind of like binomial coefficients, right? We got powers dropping down, we got factors that are dropping down by 1, 2, 3, 4, and then powers on the bottom going down by 1, 2, 3, 4. And we called that n choose k when we were looking at binomial coefficients, right? And it had a really nice closed factor. You end up with k, n choose k always has k factors, because normally there's like n factorial, but all, you get k terms down here, and then there's an n minus k terms over here, and I got a k factorial over here, and there's just more terms over here that get excluded because they cancel out. That's the closed form, but nobody actually calculates it that way. This is much more common, and you have k factors. Now, the thing to watch out for, the thing that'll throw you for a loop at first when you're doing these, is the way the notation changes between that and what we're doing here, right? Because this right here, we had like n going down, and we had k going down and n going down, right? Where n was a whole number and k is a whole number. And here, what we're going to have is we're going to be dividing by n factorial rather than k factorial. And what's happening here, so the notation changes around. What we're looking at here in these coefficients are called generalized binomial coefficients. They agree with n choose k when r and n are integers, whole numbers, positive whole numbers. But this also works when r is not a whole number, or when r is a fraction, because this goes back to just the powers and the usual rule for taking derivatives of any power function. In the same sense as you had k factors here, you can have n factors here for any particular coefficient. And I want to point out that this is the nth coefficient. R choose n is the nth coefficient in the Taylor series. Okay, that's why we're looking at this. Yeah, you can write over n factorial, but you just end up writing all the side right there when we do the calculations. This, of course, is best displayed using examples. So let's find Taylor series for each of these. Okay, I'm back to 10, and no sign of Deborah. Wait, somebody here is a pal of Deborah. Who was it? Was that like Kevin was a pal of Deborah? Yeah. Somebody here I know is a pal of Deborah, and I'd really like it if you get a chance to like check out, see what's happening with her, because it's really important, especially during this remote thing. It's really important for me to not know where people are, or if people have issues, and it's, you know, and it be whatever. Believe me, I've been dealing with so many student personal issues this week. What's another one? You know, you can only drown so bad, right? If you're already drowning, just more water is fine. Go ahead. Oh, God. Okay, so let's look at this one. Now, first of all, you have to recognize this is a binomial. It has something for the binomial. right? So the first thing you want to notice is like this is what? This is 1 plus x to the 1/2, and now it looks like 1 plus x to the k. Same way we're doing it, right? So let's take a look and see what happens on this. To be able to do the Taylor series for this binomial, first thing to notice is that r is 1/2. The next thing to notice is the nth coefficient is r choose n. And so we need to start doing some calculations on these. Okay? So let's find c sub 0. C sub 0 is just 1 always. Yay! C sub 1 is we're going to have one factor, 1/2 up top, one factor on the bottom. So C sub 1 is just 1/2. More real estate. C2 is going to have two factors, 1/2, and then subtract 1 from 1/2. What do I get, guys? In the chat, please. What happens when I subtract 1? That's right, -1/2. And this is going to be 1 times 2. Okay. A little more real estate. C3 is going to have 3 factors on the top and the bottom. Starting at 1/2 times the -1/2 that we just had, and then subtract 1 again. What do you get? Subtract 1 once again, what do we get? I'm sure someone other than Lourdes can do the arithmetic on this. Yes, that's right. And we want to keep them as fractions. We really do. Because that's going to give us a much better idea on how things are happening. -3/2. So you see what's happened? We went 1 from -1 to -3. And the 2 powers keep on going. And this is going to have 3 factorial down here now. Okay? Now, as fractions, what do I get here? C0 is 1. C1 is 1/2. C2 is what? That's -1/8, isn't it? And that's pretty easy to see. C3 is going to be a little bit tougher, right? C3, I'm seeing 1 negative is positive. I'm seeing 3 over 8, and 3 times 2 times 1. That looks like 1/16, doesn't it? Okay. So it wasn't something that's like really predictable. But there is the function now. So my Taylor series for this, I'm not going to write the general form. I'm just going to write as much these first 4 non-zeros terms, because it's just too much trouble trying to find general forms that you don't really need for the sequel. So I'm going to write this then in a really cute and clever way, because I'm not going to write the whole function, and I do want to represent how far did I go. I went to C3, so C3 is not going to be the full Taylor series. It's going to be a partial series. The full Taylor series, I just named T of X. Oh man, I got this cough going on. And again, this is not COVID stuff. Okay, yeah. This is dry throat. There we are. Okay, so this is now the full Taylor series. It's a partial series. And the way we name this, we named the partial series based upon the last coefficient, last term that you had, the power of the last term. we're going to go up to C3, which means we're going to run this up to t, the third x cubed, and so we're going to call this t3 of x. And it comes out as 1 plus, what, x over 2? Plus, well, not plus, but minus, right? Minus x squared over 8, and then plus x cubed over 16. Okay? And that got us started. Anybody spot any arithmetic errors here? I'm not seeing any, so that looks okay. All right, thanks, Lourdes. Okay. Okay. Yep, you find the coefficients, and then you just plug in the x minus a to the power behind it. Yeah, you find the coefficients, and then you just plug in the powers behind it, and you're done. Now, how about this one? Now, you see the problem here is it's not 1 plus x. However, we looked at this last time, because I can treat it like it's 1 plus x, and then do a power lift. Actually, this would be a scaled power lift. I'm going to find the sequence as if this was, I'm going to do this as if it was the cube root of 1 plus x. And then I'm going to find the series for 1 plus x, and then I'm going to replace the x with 3x squared. And that was poorly written, but there it is. That is going to replace the x. So what we're going to do first of all is we're going to find the sequence for the series for 1 plus the cube root of 1 plus x. And to do that, the first thing to do is to figure out what r is. What's r? What's the power here, guys? Somebody tell me what the power is. Somebody other than Lourdes. That's right. Cube root means 1/3 power. That's right, Timothy. Thank you. All right. I hope everyone else knows this. Okay. Yeah. And r is 1/3. So let's go looking for coefficients. See, 0 is always 1. Yay! And remember, all of the coefficients here are just r, choose n. C1, 1 fraction, 1/3 over 1. Yay! C2, and let me kind of like bring that in so you can see it now. C2 is 2 fractions, 1/3, 1/3. What's 1 less than 1/3? 1/3 minus 1. What's 1/3 minus 1? Yeah, well, that's, I'm going to do it for x, and then I'm just going to replace the x with 3x squared. Yes. And the answer is almost, David. It's negative 2/3. Okay? Yeah. But you get used to that real fast right here. And what's going to happen right there as we work these, yeah. You notice that last example, how we end up with an alternating series after the second term, right? It started positive at 1, and then positive stayed positive, then negative, positive, like that. And that was because I started out at a positive power. This one's going to alternate all the way through. Positive, positive, and then this one's going to go negative, and the next one's going to go positive. Okay, C3 is going to have 3 factors. 1/3, negative 2/3, we already did those. Now subtract 1 again. What do we get when I subtract 1 again? Negative 5/3. That's right. That's not tough arithmetic. Then again, I had a student I was dealing with last term who couldn't do that. So I don't necessarily have full faith and confidence that everyone knows how to subtract 1 on a fraction. In any case, that's divided by 6 because that's 3 factorial, right? And so let's work out those constants then, huh? That's 1/3. And this is what? That the 2 is going to cancel and end up with negative 1/9, huh? Yeah. And here, nothing cancels. I get 10 up on top. Yeah, I guess the 2 cancels. So I get 5 up on top and 3 and 4 3s. That's 81. Okay. Looking up to see if Lourdes is agreeing with me or not. Yeah. And so now, if this was this, right? And so here now, let's try this. I see my coefficients were 1 1/3, negative 1/9, and 5 81sts. So T3 of x for this function is going to be 1, wait, here we go. The third partial Taylor series is going to be 1, it's a function of x, 1 plus, what was the fraction, 1/3? And now, Ryan, what do I replace the x with here? I'm not going to plug in x. What am I going to plug in? Nope. Yeah, it's going to be x squared when the 3 cancels, yes. But in general, I'm plugging in the 3x squared here. And yeah, the 3 will cancel. And then I'm going to get negative 1/9. 3x squared squared. You see that happening? And then 5 81sts. 3x squared cubed. So I kind of skipped a step here, but I think it was important to skip that step. Because I need you guys to see that we're just doing this just as if we'd started out with a u as a dummy variable. So in a sense, this x here was a dummy, works as a dummy variable, and you just replace the real thing in when you're done. Yeah. And so let's take a look at what this came up with. T3 of x here is 1. The 3 cancels, I get plus x squared. Right? Plus x squared. On this one, I'm going to get a 9 canceling. The next one, on this next one, I get a 9 canceling. I get negative x to the 4th. Yeah? On the next one, I get 3 of the 3's canceling in 81. And it looks like 5/3 x to the 6th. Okay. Because of the substitution, negative x to the 4th. Okay. Yeah, that's right. And then I get 5/3 x to the 6th, right? So, guys, I was working with the T3 of x when it was 3x, when I was plugging in x, right? What's the highest power that shows up here, guys? Never ever will we have fraction powers in here. What's the highest power that shows up when I get these first four non-zero terms? That's the whole point of Taylor series. Oh, I see what you did. Okay. Yeah. Negative x to the fourth over, okay, that's no problem. Thank you, Lourdes. Yeah. Guys, I was looking at the four non-zero terms, and I was thinking it was T3. Guys, what's the highest power of x that showed up in this expansion? What's the highest power of x that showed up in this expansion? Everybody see this? 6, yeah, right? This is not, and this is something that I've had issues having to straighten out my tutors on. Not Alex, I don't think. I had another tutor that had issues with that. This, what's the highest power that shows up? This is, even though this is the first four non-zero terms, and expanded off of, coming off of the x cubed, I'm looking at C3. This is now T6 for this power. Because the partial series, all the other ones that are missing right there, they're still there. They just have coefficients of 0. So on this expansion, C0 is 1, C1 is 0, C3 is 0, C5 is 0, on like that. Yeah. And want to pay attention to that, okay? And so I'm going to highlight that somehow or other, right? Okay? So I'll leave notes like that. It should come out okay. Now, here we go, guys. One more example on these before we move on to the fun stuff. Okay. And I have you guys till 10:30, right? Yeah. Moving from the one class to the other class is weird. I have a 9:10 to 11. I got a class that starts at 9:10, and I know when I got with you guys last time, I got that confused. I had another hour or so, another 40 minutes, when it was actually 10:30, time to stop. Oh. Getting my head straight. Move from 100 an hour, 120 minute to 100 minute lectures. So here we go. So how about this one, guys? Obviously, I'm going to do this as 1 over 1 plus x. And I can think of it like 1 over 1 plus u, but I'm going to keep on doing the standard thing. Okay, this is 1 plus x to the negative 3, except that x is actually x squared. Okay? And now we do the usual things. Identify the radius, the r as 3. Not radius, I'm sorry. And now we're going to go ahead and find the coefficients. Let me lock this thing down so it's not moving around like that for you. So remember that on the binomials, the nth coefficient is r choose n. And you don't worry about the formula so much as how many factors, right? So let's do this. C0 is 1, always. C1 is negative 3 over 1, yeah? C2 is negative 3 times, it's 1 less than negative 3. 1 less than negative 3? Somebody's up there paying attention. What's 1 less than negative 3? I've lost my ability to subtract 1. Thank you, Patrick. -4, right? And then C3, -3, -4, -5 over 3 factorial. Kill the 3, kill the 3, kill the 2, leave a 2. Kill the 2, leave a 2. So there we go. Let's simplify those. C0 is 1. C1 is -3. C2 what? Why is there? Oh, that's right. C2 is just 6, right? Yeah. C3 is negative, negative, negative is negative. No. That was negative, negative, positive. There we go. Negative, negative is negative. Then 2 times 5 is 10. 1, 3, 6. Yeah. Positive 6, that guy. So I got 1, 3, positive 6, negative 10. Sweet. Okay. And we see it's actually truly alternating from the beginning. So now I'm ready to write my polynomial, t of x. And because we did this, right, we know it's not going to be the same thing, right? We plug in x squared. We're going to be plugging in x squared, normally plug in x. So once again, we're going to end up, by the time I get to the C3, t to the 6th. But I'll fill in as soon as I'm actually there. I get t question of x is 1 minus 3x plus 6x squared is 10x cubed, except that none of the x powers is right. So I'm plugging in x squared. X squared is x to the 4th. X squared to the 1st squared. Squared is x to the 4th. Squared cubed is x to the 6th. And so when we get t3 of 6. Now, there's another finicky little point that we're not going to worry about a lot. I wanted to point out, okay, the radius in the binomial series is 1. The radius of convergence of the binomial series is 1. But wouldn't it be 6? Where? Oh, yeah, that's right. See, I'll spot that before I spot chat. Okay. Yeah. The radius of convergence on the binomial series is 1. If you do the substitution, because what ends up happening is this x. I wanted that x to be less than 1 for radius. Right? And now I want 3 squared to be less than 1. Here and here. So it makes a difference, right? The rate changes depending upon the substitution. Okay? That's just how it works. But in practice, we're not talking about that a whole lot. Yeah. Okay, promise time. Okay. Now we're going to do Taylor series and the proof of the Euler Identity. Yay! Now, let's make like see only the part that's important first, then we'll expand it so we can cover this stuff. Now, in general, the Taylor series is coefficients times powers of x minus a. 1 plus 1 x minus a. The audio is going to chop a lot. That has a way of coming in and out. And so I'm on talking until people tell me to stop chopping. How about that? So I'm going to kind of like talk for a while and about nothing in particular, hoping that the audio will stop chopping and you'll let me know that you can hear me again. So I'm continuing to talk, hoping the audio is going to stop chopping so you can hear for me. Thank you, Ryan. Okay. And yeah, it's just waiting for the congestion to stop. I told you I lost like 30 seconds of video earlier this week. The video just went black. So it chopped out the video too, which is really nasty. I can handle the delays, but when the video just totally disappears, that's tough. And I've seen it wait like 15 seconds. I've seen it chop, a 15-second chop, just waiting for it to refresh when I move from page to page too. But I'm sure all this is going to improve as people recognize and bring in more servers and the backbone gets stronger. Everybody had to do this. In any case, so there we have. We have coefficients times powers of x minus a. 1 plus c1 times x minus a plus c2 times x minus a squared. And the real thing here is we just need to find c sub n. And c sub n, by the presentation we've always looked at here, is what happens when you take the nth derivative, plug in a to make everything else go to 0, and then divide by n factorial because that's how much has come out multiplying c sub n as I'm calculating it from looking for coefficients from derivatives, as we've done twice now. Okay, so the idea here is the real thing, I mean, the thing that makes the Taylor series work is calculating these coefficients. Now, for the binomial series, we know what this coefficient is, just r choose n. In general, it's going to be the nth derivative at a, or wherever we're centering, divided by n factorial. So what we're going to do, to find the Taylor series, we need to find in the nth derivatives, plug in a, and then divide by n factorial. Once we have the coefficients, we'll multiply by x minus a to the n, or just x to the n if we're centering at 0. And for the next 3 examples, which are all related, I'm going to be centering at 0. And these are nice because their derivatives eventually wind back on top of themselves. So let's start with the cosine. And I'm going to look at 0, 1, 2, 3, okay? The nth derivative, well, n is 0, the derivative is the original function. The 0th derivative is the original function. That's before we do any derivatives. And so, for the 0th derivative, is just the cosine itself. Okay? And now that we've identified the derivative, we can plug in 0. What's the cosine of 0, guys? Remember, the sine of 0 is 0, so the cosine of 0 must be... That's right. That's right. That one's 1. Everybody can say 1, right? I got 10 people in here. I see one person answering. Guys, what's the cosine of 0? Everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 7. 1, 2, 3, 4, 5, 6, 7. I got like 3 people who are like, I don't know, listen to music or something. I'm just kidding. But yeah, okay. Yeah, okay, kind of paying attention. That's 8. Still missing anything from Osmaldo. Osmaldo, you still there? Because I know that's happening. I'll finish these sequences, these series, these things right there, and there'll be 1 or 2 students in my MAC 1147 who just never say goodbye. They're just kind of there. God knows how long it's been since they were paying attention to it. And so I got 2 students who aren't listening. Okay, that's upsetting. Okay, in any case, yeah, it's 1. Okay, so let's take the first derivative. What's the derivative of cosine, guys? What's the derivative of cosine? Negative sine. That's right, Patrick. That's one of the easy things, right? Okay, what's the sine of 0? Sine of 0? Yep, yep, yep. Everybody's got that one. That's easy. That's our base of our second derivative. Negative cosine. Well, we just answered that, right? Cosine of 0 is 1. So that's negative 1. Third derivative? Third derivative? Well, it's going to be negative sine. No, positive sine. And we know what the sine of 0 is, right? 0. And the fourth derivative is right back to where we started. And that's how it is with sine and cosine. The fourth derivative is right back to where it started. And so we can actually see this thing repeating, right? And what you see here is the even powers. The even powers, it's either 1 or negative 1 alternating. And the odd powers, it's 0. Right? And so all that's missing is divide by n factorial on 1 and alternate. So the cosine is going to be 1 for c sub 0. And c1 and 3 and all the odd ones are 0. And c2 is negative 1 over the 2 factorial. And c4 is 1 over the 4th factorial. Okay? And because I won't look at the full series, I'm just going to say minus. Erase. Minus dot dot dot. That continues on forever. If I'd stopped, that would have been T4. The 4th partial series for cosine. So I'm just going to stop at 3. Let's do that at for sine now, okay? For n equals 0, wait, erase. The 0, erase. The 0th derivative, first derivative, second derivative, third derivative. Okay? Because I know the 4th derivative is going to go right back to the original function. So, for sine, the 0th derivative is just itself. Sine of 0, guys, you find numbers for all of them, and then replace x or x minus a. That's exactly it, right? Yeah, it's 0. And yeah, I'm going to find f out of 0, but remember the actual coefficient. Remember the coefficient here? Yeah. Needs an n factorial for c sub n. Right? And so, the derivative of sine is cosine. Yeah. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And then the next derivative is just back to sine again. Sine of 0 is 0, cosine of 0 is 1, 0, 1. And you can see what's happening this time. This time the odd powers are 1 or negative 1, and the even powers are 0. I'm doing a little cleanup on the side that you're not seeing. So I didn't like the way that looked. 1, 2, 3, negative sine, negative cosine, positive sine, 0, 1, 0. Okay, and as versus for the cosine function, we saw the evens gave us power and the odds dropped out. Okay? So looking at both together, I see the cosine gave me the even powers, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then the sine function, right, is going to give me the odd powers. So instead of starting it with a constant, it's going to start out with an x. Positive minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. That's the first three. Now, one thing I haven't done here is I haven't looked at the radius. I haven't looked at the radius. And the answer is the radius on all these is infinity. These are true for all x, which is really wild. Look at this polynomial. This is like 1 minus x. You say, first of all, the radius is infinite, and that's pretty easy to see, right? No matter what value of x is, the factorial is going to beat it, because polynomial versus exponential, right? How else can you see that this is infinite? This is always going to converge. I want to point out that for any value of x, right, x to some particular power over that n factorial, yeah, that's eventually going to go to 0, right? X to the n over n factorial, yeah. It's just going to be 0. That's all there is to it. So the nth term goes to 0 and alternates, and that's enough to say that these have an infinite radius. That's always in there. And so we have these are full series. Now the thing that's really odd when I'm looking at this thing, and this is just kind of bizarre even to me, I look at this and then I remind myself, this thing's periodic. That means that as these things go up and down, if I replace this with, and this is equal to the cosine of x plus 2 pi. If I replace all the x's here with x plus 2 pi, I get the same series. Really bizarre fact. I'm going to take that out of the notes because I just wanted to let you have an idea that there are some things which are still very profound that even the professor finds it really just strange and difficult to see intuitively. Okay, now let's look at e to the x. How about we just cut to the chase on this one? All derivatives are e to the x, including the original function, right? And what is plug in 0? What do you get? What's this when I plug in x equals 0? Yup. All the coefficients, all the nth derivatives at 0 are 1, and so all of the coefficients is that 1 over n factorial. And that leads us to this expansion, x to the n over n factorial. Now, the last slide in our notes from Tuesday said I would take care of this later, and now is later. So the x to the n over n factorial, that is the expression for for e to the x. So we have here is that e to the x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. There's a reason I'm doing this. Plus x to the 5th over 5 factorial. That's enough. That's 6 terms from power 0 to 5. Now, guys, this is true for any power. Any power. X going to be a whole number or a fraction or a negative power or 0 or even a complex number. In particular, it's true for e to the ix. So let's replace everything with ix. 1 plus ix. What's I squared, guys? What's I squared? I squared? I squared? What's the different definition of I? Yeah, -1. So it's I squared x squared over 2 factorial and that should begin to look kind of familiar, right? Plus I cubed x cubed over 3 factorial. What's I cubed? What's I cubed? -I. What's I to the 4th? What's I to the 4th? I to the 4th, anybody? Yep. And now, what's I to the 5th? What's I to the 5th? I. Okay, so let's take a look. This is 1. Let's just look at the real parts. Just looking at the real parts, I see 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and that's kind of like seeing what's going on, right? Minus ... And this is going to be plus I times what? X, the imaginary part, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus ... And now, yep, and the other one looks a whole lot like sine x. This is indeed the Taylor series for cosine x. And this is I times the Taylor series for sine x. And the Taylor series converges to the function inside its radius of convergence. And its radius convergence is infinite for all x. And so we have now, guys, e to the I x equals cis x, the Euler identity. Yay! And I don't know if anybody was in here with me in Trig or something like that. I think somebody did. So like however long that was, maybe a year ago or so, I made that promise to you that I would teach you this, that I would prove it. There you go. Now it's proven. And we've got 10 minutes left for a couple more examples, or as many as I can get in. Yeah? So that was pretty cool, huh? Yeah. I didn't have to use Taylor series to prove it. It's actually possible to prove the Euler identity other ways. But boy, it's just so much easier with the power tools of the Taylor series. Okay, let's try the Taylor series for these at particular values, okay? Just so we get some practice. And here's just a polynomial, okay? So here we go. Let's do the things. N, Fn of x, Fn of a, at a. Okay, so for the 0th derivative is the original function. And what is this at a when a is 1? In this case, because I'm looking at expanding at 1, we're going to plug in 1. Can I expand log x, cos x, etc. with the power series, or must you use Taylor's Harmony? Now, one of the other things that's true is anytime, and yes, you can always use the standard Taylor algorithm that we're doing right now for log x, cos x, etc. As a matter of fact, I did that for log x, remember? And I took the derivative, and then I found the coefficients. So it was the other way around. Yeah, you can do this directly, but the cool thing is anytime you can get a power series using any method, even if it's long division or multiplying two previous series that you knew, as soon as you get a Taylor series, it's unique. I took derivatives in there, yeah, but you can use any method. As soon as you're at a power series, it's the Taylor series. And that's all you have to worry about. But in any case, let's go ahead and get this example in so you can see it, okay? Is that cool? All right. What's this? What's the function itself at 1? What's the value of the function at 1? Anybody? What's the value of the function at 1? Yep. Let's take the derivative. First derivative, 1 plus 2x. What's the value of the function of the first derivative at 1? Same answer, yeah. Let's take the second derivative. What's the value? 2. Third derivative. And all further. Yeah? So there we go, guys. Remember to find the function itself. The Taylor series for this function at 1, expanded at 1, is the coefficient. Well, they're over 0 factorial, plus 3 over 1 times x minus 1, plus 2 over 2 factorial. I'll write this right over 0 factorial, 1 factorial. Nah. And this is going to be over 2 over x minus 1 squared over 2 factorial, right? Or I can write this as x minus 1 squared plus 3 times x minus 1 plus 3. So in a sense, we use this right here to do a shift on the original polynomial. Yeah. And we've got like 5 minutes. I can do another example. And that was the last example. And the timing, I was right. These things happen every once in a while. I had more things for estimation, and it just timing it out myself on the side, it wasn't going to fit into the lecture, and that's why it moved to the other lecture, and I had to make the painful choice to get rid of the polar. Okay, so let's look at this one. Same way, guys. We're going to create the table, and then when we finish right there, we'll divide by n factorial and multiply by the power. So n, the nth derivative at the value we're expanding around. 0, 1, 2, 3. Just get the first 4 terms. That's enough. Okay, so here, for the first derivative, just root x, yeah? Or x to the 1/2. And what's the derivative at 4? What's the function at 4 is 2, yeah? The first derivative is 1/2 x to the negative 1/2, yeah? And at 4, what's that equal to? Somebody tell me what that's equal to at 4? What's the first derivative at 4? Yeah, that's right, Lourdes. And while you're doing that, okay, and what's the second derivative at 4? I'll do a little bit of the arithmetic on that for you. There you go. The 1/2 power of 4 is 2. The 3/2 powers is 2 cubed. So that's 1 over 4 times 8 is 32. Check. Kayleen checks me. And then we get what? 3/8 times 1 over 2 to the 5th, yeah? So that's 32 times 8, 256. 3 over 256. Okay, so here we go. My Taylor series on this, or at least the third Taylor series, or the third partial anyway. And that's what I should have written over here. But I didn't worry about the other one because that was it. That was everything. The third partial is going to be 2 plus 1/4. I mean, the 2 is times x minus 4 to the 0. Now it's x minus 4 to the first. And now it's over 1 factorial. Minus 1/32 over 2 factorial. X minus 4 squared plus 3 over 256 x minus 4 cubed. Don't forget the factorial. 3 factorial. Okay, so as I'm looking at this, let me clean it up a little bit. 2 plus 1/4 x minus 4 minus 1/64 x minus 4 squared. The 3 cancels, I end up with a 2. 1 over 512 x minus 4 cubed. And there would be more powers. This is why I call this one T3x. Yeah. And I'll kind of stop there and make sure that everybody agrees with my arithmetic. Did my arithmetic check the rest of you guys? I just wanted to get that cleaner. Okay, that looks good. Hey, so Lourdes is happy, I'm happy. All right, guys, that finishes us up plus 7 seconds, right? There you go. So I hold off on the estimation problems until you need to. Now that I know how much we've covered here, I'm going to get you 5 questions for a quiz tomorrow. I'll load that up tomorrow, assuming things don't go crazy on this, and spend the weekend going crazy grading stuff, including your class and other classes. All right? So you guys got a back that I need to take care of, and I'll go on from there. All right, guys. Thank you so much. Goodbye. Stay safe. Remember, elbow bump is a new air kiss, right? Take care, and we'll see you guys next week then, right? Okay.